First, it's key to understand the difference between a dependent and independent variable. So first, a dependent variable is one that depends on the movement of the independent variable. So by movement, I mean if the independent variable is increasing or decreasing, it can predict the dependent variable. And the dependent variable is always going to be shown on the y-axis of a two-dimensional plot. Whereas the independent variable is the variable that's used to predict the outcome of the dependent variable. The independent variable is always shown on the x-axis. So a great example of this, and one that's very basic, is if you're looking at the relationship between the age of an individual and time, your time would be the independent variable, so along the x-axis, and the age of the individual, because it depends on time, age would be shown on the y-axis, and that would be your dependent variable because age depends on time. So the first measure that we're going to look at is called covariance, and covariance is a very basic measure, and it only tells you the direction of the relationship. So how does the x and y variables vary together? So either you can have a positive covariance, which would tell you that your variables, your x and y variables, will increase together, or you can have a negative covariance, which would indicate that as the y variable increases, your x variable decreases. Or you can say it opposite, that as the x variable increases, your y variable decreases. And this is called an inverse relationship. The two most common types of correlation, or measures of correlation, are called Pearson's correlation coefficient and Spearman's correlation index. Pearson's correlation coefficient is used to understand the relationship between the x and y variable, and it uses the actual raw observed values of your data set. On the other hand, Spearman's correlation index is very similar. However, it uses ranked ordered values instead of the actual raw data that you observed. And its benefit is that if you have data that isn't normally distributed or contains outliers, the outliers don't influence the correlation index because you're taking those raw data values and ranking them. Thus, the outliers don't have as much influence over the result. And in this case, the Pearson's and Spearman correlation values will not only tell you the direction, but it'll also tell you the strength of the relationship. So as I sort of mentioned before with the covariance measure, direction is how the x and y variables move together. So you can see in the picture there that a positive correlation would show that as the x variable or the independent variable increases, your dependent or y variable also increases. And again, in the picture, if you look at the negative correlation, as your x or independent variable increases, your y or dependent variable decreases. And then if you have a neutral correlation, it just means that the x and y variables don't seem to co-vary or move in any direction together. And second, the strength of your correlation value from Pearson's or Spearman tells you to what degree the variables actually move together. So again, in the picture, you can see the perfect association would be one where the variables can be drawn on a line. So you could draw a straight line and it would cross through every point in your graph. Whereas a strong association would be one where the points don't necessarily, you can't necessarily draw a line through all the points, but all of the points are very close to that line that you would have drawn. A weak association is one that the points seem to still be following a trend, either positively or negatively, but are very spread out from the line that you would draw through the middle of those. And then in the last case, where it's no association, you can see that there doesn't seem to be a trend. It's just kind of a blob of points. So in this slide, it shows an example of how to actually calculate covariance. And I'm not going to go through the math, but you can look at it and see that it is fairly simple to calculate. And it also gives you a very simple answer where it just shows you if it's positive or negative, showing you the relationship of the two variables. Again, here we have the Pearson's correlation coefficient, which is indicated by the letter R. And you can see how to calculate it there. And again, I'm not going to go through the calculation because in reality, when you're using these correlation coefficients or indices, you're never going to be actually calculating them by hand. You're probably just going to be using something like R to calculate them. But you can see how to actually interpret the Pearson's correlation coefficient, where the positive or negative sign indicates the direction of the relationship, so either positive or negative. A 0 indicates that there's no relationship between the variables. A 1 is a perfect positive relationship between the variables, and a -1 is a perfect negative relationship between the variables. Whereas 0 to 1 indicates kind of the strength, so weak, moderate, or strong, or 0 to -1 is still weak, moderate, or strong in the other direction. And it's also key to note that a perfect relationship between two variables, so 1 or -1, is almost never going to happen in real life. The time versus age example would be one example of a perfect relationship, obviously. However, if you're looking at any other sort of variables in nature, you're almost never going to have a perfect relationship between two things. So if we use a economic growth percent and compare that to S&P 500 returns percent, which is a stocks type of measure, and we look for the correlation between those two variables, we can calculate this, as you can see, and the Pearson's correlation coefficient is 0.66 in this case. So 0.66 would mean that the relationship between the economic growth percent and the S&P 500 returns percent is relatively strong or moderate, somewhere in the moderate to strong relationship. And it's a positive relationship. So as economic growth percent increases, so does your S&P 500 returns percent. One very important thing about correlation analysis is that just because you have a high value or any value at all other than 0, it doesn't mean that the independent variable is actually related to the dependent variable. So we can have things that are called spurious relationships, where there is a relationship between the x and y variable, but it's not expected, or it's a false relationship, or it's fake. It's just random chance that these two variables are related to each other. In reality, they're not actually related at all. So a funny example of this is if you plot the relationship between the number of people who drowned by falling into a pool, and you correlate it with the films Nicolas Cage appeared in, you would see that there is actually a correlation between these two things, and it's fairly strong. It's 0.66. So you can see here that obviously Nicolas Cage being in a number of films has nothing to do with people falling and drowning in a pool. Unless, of course, they watched his movies and decided to jump in the pool and drown. And again, here's another example where there's a correlation between per capita cheese consumption and the number of people who died by becoming tangled in their bed sheets. Obviously, these things have nothing to do with each other, but you can see they're highly correlated at 0.94. So then what can the correlation actually tell us? Well, there's kind of two things. First is if the two variables that you're looking at are linearly related to each other. So if it's not a zero value, then you know that there is some sort of relationship there. It doesn't have to be a strong relationship to tell you that there is some sort of force that is causing your independent variable to correlate to your dependent variable. Correlation can also be used to understand the strength of that relationship or the direction of that relationship. So as x increases, does the y variable increase or does it decrease? And you can also see the strength, so how much do these two variables actually vary with each other or co-vary with each other? And on the other hand, what can't correlation tell us? Well, first of all, how the variables are actually related. So a correlation value will tell you the strength and direction, but it's not going to explain why the independent variable is actually related to the dependent variable. It also can't be used to actually predict the outcome of the dependent variable based on a value on the x-axis. So if you provide the value of the independent variable, hypothetically, you can't calculate the outcome of the dependent variable. Correlation also can't tell you the causation. Just because your x and y variables are correlated, they could be very strongly correlated with each other. It doesn't mean that those two variables are actually related in real life. The other thing, again, to kind of connect back to an earlier lecture, is that even if you have a correlation at the population level using your data or a sample even, you can't then say, well, this is true of the sample or the population, thus the individual has this exact characteristic. You can't do that. That's an ecological fallacy. So if you're seeing that there's a correlation between the temperature outside and the desire to swim at a local pool, and you see that the hotter it is, the desirability of swimming goes up, it doesn't mean that your friend enjoys swimming when it's hot. Now, to move on to regression analysis, we can understand the relationships using a mathematical basis, and it gives us a lot more information about the relationship between the independent variables and the dependent variable. So when we create a regression model, we're actually creating a mathematical model that we can then use to predict either the x variable based on a given y variable, or value rather, or we can predict the y value based on a given x value. There are different types of regression models. and they can be used in different ways. However, for the purpose of this course, we're going to focus on linear regression models. So only models that can be explained using a perfectly straight line. Linear regression is sometimes known as either bivariate regression or multivariate regression. So bivariate means two variables, because bi means two and variate means variable. So a bivariate regression model is describing the relationship between one independent variable and one dependent variable. Whereas if you had a multivariate regression model, you'd be looking at multiple, so two or more independent variables and one dependent variable. In regression modeling, you're always going to have one dependent variable, but you can have as many independent variables as you want. So to reiterate the difference of a dependent and independent variable, the dependent variable, again, is always on the y-axis. It can also be known as a response variable because it's responding to the changes in your independent variables. And the dependent variable is also the variable that you're actually interested in. And the independent variable, again, is always on the x-axis. And it's also known as either a predictor variable or an explanatory variable because it's explaining or predicting the outcome of the dependent variable. So the way we represent a bivariate regression model is through this equation. So y equals italicized b plus italicized bx. And this is the sort of academic equation, but when I personally learned it in high school, we learned y equals mx plus b. So you might have learned something different from high school, but this is sort of the academic approach to the equation, where y is your dependent y variable, so the value or the predicted value. The x variable is the value of your independent variable. The b1 is the slope of the line of best fit, and your b0 is the location on the y-axis where your line of best fit actually intersects the y-axis when x is equal to 0. So we can use this simple formula to create a regression model based on data points. So in this example, we're looking at the black line, and at the y-axis where x is equal to 0, the coordinate of the black line is 0, 10. So 0 on the x-axis, 10 on the y-axis. And then the last point, or the rightmost point on the black line, is 5 on the x-axis and 20 on the y-axis. So using those coordinates, we can create the regression model. And through the math listed there, you can look through it, very simple. Our final regression model will be y is equal to 10 plus 2 times x. So based on that, we can input either a y value or an x value to predict the other variable. So most commonly, you'll input an x value to predict the value of y. So we can use this formula to predict a value of y based on an inputted or given value of x. So in this example on the slide, we are trying to determine the value of y where x is equal to 4.5. So you're simply inputting 4.5 in place of the x and doing the math to determine that y is equal to 19 when x is equal to 4.5. You can also do it the opposite way, so you can predict x given a value of y. So if we input the 19 in place of the y, and solve for x, you can see x is equal to 4.5. So it's important to understand that in real life, you're almost never going to have a perfect relationship between the x and y value. So where the Pearson coefficient value is less than 1, so the absolute of it, so the absolute of a value, if you remember from high school, means that if it's positive, it stays positive. If it's negative, it converts to a positive value. So if you had -1, the absolute of -1 is just 1. Or the absolute of +1 is just 1. And the absolute of -0.5 is 0.5. So if your absolute value of the Pearson or Spearman correlation coefficient is less than 1, we don't have a perfect relationship, and thus we can only use the regression model to estimate different x or y values. And when we do that, there's going to be an error associated with our prediction. And the closer your Spearman or Pearson correlation coefficient is to 0, so where there's not really a relationship between the x and y value, your predictions are going to become less and less accurate. So the regression model is basically used to describe what is known as the line of best fit, which in this picture is the red line. And you can see the points that are drawn onto this scatter plot in blue, that they're not all aligned along the red line. You can see the green arrows are showing what are known as residuals. So the line of best fit, also known as the regression line, is the line in the graph that has the lowest cumulative error. So it's basically an average of where all of the points are, and it's trying to have the same amount of distance between each point and the line on both the top and the bottom. So it's sort of an average of all of the points. So when we plot real data onto a scatter plot and calculate a regression line, it's almost impossible to have the regression line intersecting all of the points on your graph. So in this case, we have a regression line that's shown in red. We have points that represent your data points or data values for the x and y variable, and they're shown in blue. And the green arrows, which are not shown for every single point because it would be confusing. The green arrows are indicative of the residual or error between the actual observed point and the line of best fit. So the line of best fit is our regression model, and it's trying to take an average or trying to reduce the amount of error in the model. So the error or residuals are the distance from the regression line to the actual point on the graph. And this is the vertical distance. It's only being measured on the y-axis. So a residual, to be clear, is the difference between the observed data, so the points on the graph, and the prediction of that point, which is the red line or the line of best fit or the regression line. So there's measures that we can use to understand the fit of a model. So R² will measure the goodness of fit, or how well the regression line actually approximates the observed data points. So how much error is actually in the model? So are the points very close to the line of best fit, or are they very far apart? And just a general note is that R² is very different from Pearson's or Spearman's R. It's not simply taking Pearson's or Spearman's R and actually squaring it. It's something completely different. So we can calculate R² using the following mathematics. However, I'm not going to go through it. You can go through it on your own, but I'm going to show you in R that it's very easy to calculate R². You don't have to do it manually. And if R² is 0 in the end, it means that there's no relationship between the x and y variable. And on the other side, if your R² value is 1, it means you have a perfect relationship between the x and y variables. And an R² of 1 would mean that your regression line is intersecting through all of your points on the scatter plot, and it's almost impossible in real life. In fact, if you have an R² value of 1, it's more likely that you have an error in your data or an error in your code, because a relationship so perfect is almost impossible. Now, as I was talking about in a previous slide, you have bivariate models and you have multivariate models. So a bivariate model would be one dependent variable and one independent variable, and you can use R² for that. But if you have a multivariate model, so you have one dependent variable and multiple, so 2 or more independent variables, you'll have to use adjusted R². So adjusted R² essentially accounts for the addition of more predictor or more independent variables in your model. Because the more predictor variables or the more independent variables that you add to your regression model, the more your R² value will increase. It doesn't actually matter if the relationship or the prediction accuracy of your independent variables increases. It's always going to inflate the R² value based on the math that you're doing. So we can account for this by using an adjusted R² model, which accounts for the addition of more variables in the model. Your adjusted R² value is always going to be smaller than your R² value, and your adjusted R² can also be negative in some cases. And on the right there, you can see how to calculate R² or adjusted R² and how it compares to your R² value. So the fact that an adjusted R² value is going to be smaller than your R² value, and by how much, depending on your sample size as well as the number of variables in your model. So as I kind of said in the last slide, you use an R² value when you are doing a bivariate regression model, so one independent and one dependent variable. And then you use an adjusted R² value if you're doing multiple regression or multivariate regression modeling, so one dependent and 2 or more independent variables. And we need to use adjusted R² because as you increase the number of independent variables in your model, it's always going to increase your R² value independent, or it doesn't matter that the addition of that independent variable is actually adding explanatory power to the model. It's always going to increase that R² value. So the addition of 2 or more independent variables means that you have to use adjusted R² to account for the addition. So now that you understand what a regression model actually is and how it functions, we can move on to an example and how to interpret the results of a regression model. So in this example, we're using data from IMDb, the Internet Movie Database, and we're looking at the relationship between the average review out of 10 and the budget of the movie. So in this case, the dependent variable is the average review of the movie. So what did people rank the movie out of 10? And the amount of money they spent, the production spent on or to create the movie on the independent variable or on the x-axis. So you can see here, there are many movies that were made for relatively cheap, and then you have a few that spent a lot of money. And you can see there's a positive relationship between these two things. You can also see that this is real data, and the relationship between the two variables is not always so clear. But you can see that based on the trend line or the regression line, that there is a trend upward. So when you're using RStudio and you're looking at regression with a bivariate regression model, this is the output that you'll be looking at. So on the very first line, there is the call, and that shows you the regression model that you used. So LM is the function to create a regression model, and the formula equals means that average vote, so that's our dependent variable, is equal to the budget USD, which is our independent variable. And you have to use that little squiggly, it's I think called a tilde, and that represents the equal sign in the model. And then you have data equals budgets. So I'll show you in R that the budgets is our data frame that we're working with. Average vote is dependent variable, and budget USD is the independent variable. So I'm going to break down each of these different things in a separate slide so you understand it and you can work through it with me. So the first thing is our residuals. So this is, again, the vertical or y-axis difference or error in the model, showing the predicted value of the regression model and the distance to the actual observed value. So the residuals in the regression summary is shown as a interquantile range. So it shows you the lowest value, the largest value, and then the first and third quartiles, as well as the median. So in the context of this data, our residual represents the difference between the actual review score of the movie and the predicted review score of the model. And there's a few things we can gather from looking at the residuals. So on the low side, the minimum residual is negative 4.4. This tells us that for one of the movies in our sample data set, there's a difference of negative 4.4 review score points, so out of 10. So you rank a movie 1 out of 10, so 1 through 10. And the predicted value from the regression model is 4.4 review points away from the actual observed review score of that movie. So in that case, it was a very bad prediction by the regression model. And if you went back to the scatter plot with the regression line, you can see that some of those movies are being predicted very poorly. In this case, when the residual is a negative value, it means that the regression model has over-predicted the movie's review score. We also know that 50% of the data, or 50% of the residuals, are between negative 0.5 and positive 0.6. And that's good because that means that our median in this case is 0.09, and our median should be close to 0. And in this case, it is quite close to 0. And this suggests that the residuals follow a normal distribution, which is important because it's saying that the model on average isn't over or under predicting any one movie. So next in the summary of the regression model, we have the coefficients. This is kind of the meat and potatoes of the regression model. This is the thing that actually tells you what the model actually is, the mathematical model. So first of all, we have the intercept. It's in brackets. It says in brackets intercept. The estimate is the actual value where the regression line intersects with the y-axis when x is equal to 0. So when the budget of a movie is 0, a review score for a movie will be 5.8 in this case. It doesn't always really make sense, but because you're using it to predict the budget, or you're using it to predict the review score where the budget is equal to, say, $1 million, you're adding that review score of 5.8 to any prediction. And for the budget USD, the estimate is 0.0000, however many zeros, 2160. So that means that for every $1 increase in a movie's budget, the rating of the movie will increase by that value. And we can use this information to construct the final regression model, and we can then use it to predict the rating of a movie based on its budget. Or we can predict the budget of a movie based on its movie rating. And as I sort of discussed previously, regression models have error associated with it, and our standard error tells us how much error is associated with each estimate. So, for example, the intercept estimate is 5.830. Our standard error is 0.044. Thus, our intercept actually is somewhere in the range of 5.786 to 5.874. But for the purpose of the regression model, you would just use the 5.829 or 5.830, and you're just cognizant of the error associated with that value. Now, the t-value is somewhat less important. It can be important in certain circumstances, but it essentially just is saying the larger it is relative to the estimate, the more significant your outcome, the more statistically significant your outcome. And it's used as a means to calculate the significance of your estimate. Now, the PR, and then in brackets, greater than the absolute of t, is the probability of observing a larger value than the absolute of the t-value. So this is the chance of committing a type 1 error, or also known as the significance or your p-value. So can you trust your result? And RStudio uses asterisks or a period or a space to indicate the level of your p-value. You can actually just read the p-value. However, in most cases, it's easier just to look at the symbol beside it. So 3 asterisks represents a p-value less than 0.001. We would consider that very significant. 2 asterisks is a p-value less than 0.01. I would still consider that very significant. If it has 1 asterisk, that's a p-value less than 0.05. And as I talked about in a previous lecture, a p-value less than 0.05 is technically statistically significant, and there's nothing wrong with it. But as I discussed, it's really not an ideal p-value. Period represents a insignificant outcome, which in this case is a p-value less than 0.1. And nothing, just it won't show anything. It'll just have nothing. That represents an insignificant outcome where the p-value was greater than 0.1. And the statistical significance tells us whether or not we can reject the null hypothesis that the independent variable has no influence on the dependent variable. So in other words, if the variable is statistically significant, we know that it's having some sort of measurable influence on the dependent variable. And another thing I want to talk about with significance is if your p-value is 0.051, so it's very close to being a p-value less than 0.05, you can't then say, well, it's a very close to being significant. It's just, it either is significant or it's not significant. There's a cutoff that is 0.05, and if it's above that, even by a fraction, it's just not significant. And it's bad science to say that it's approaching significance or it's very close to being significant. It's just, in that case, not significant. Now, the last 3 lines of our summary regression output tell us about the residual standard error, the multiple R-squared and adjusted R-squared, as well as our F statistic. So the residual standard error tells us on average the variation between the predicted value and our observed value. So if we take the average of the movie ratings of all movies in the dataset, it is 6.01. That means that on average, you have a movie rating of 6.01 plus or minus 1.069, because our residual standard error is 1.069. So you have to either add or subtract that from the average movie rating. So our average movie rating is actually somewhere in the range of 5 to 7. The standard error, or the residual standard error, can also tell us about the percent error in the regression model. So if we look at the standard error and divide it by the average movie rating, in this case, we know that there is 17.8% error in our regression model. Now, as I discussed prior to this, we have the multiple R-squared, which is simply just R-squared, and the adjusted R-squared. And you can see that the R-squared value is 0.0977, and our adjusted R-squared is 0.09648. Now, in this case, because it's bivariate regression, we don't need to look at adjusted R-squared. RStudio will just always output the adjusted R-squared. So in this case, you can just look at the R-squared value of 0.0977. Because we're using real data, our variables aren't always going to have a good relationship. In this case, our R-squared is actually very low. The relationship between the budget of a movie and the average rating of a movie doesn't actually seem to be very related. So in this case, 0.0977 suggests that the budget of a movie can only explain 9.77% of the variation in an average movie rating. The F statistic at the bottom is another kind of difficult to interpret value. So simply this basically just means that the further this value is from 1, the better. And it's sort of similar to a Z or a T or a Z test, but it follows an F distribution. And for the purpose of this course, the F statistic is not really needed or necessary to look at, but it is used in certain circumstances. So the last thing we're going to talk about is the assumptions of linear regression. So the assumptions of linear regression are there to inform you if you break any of these assumptions, your regression model is not going to be performing as well as it should be. So the first assumption of linear regression is that your model can be actually predicted using a linear regression model. So in the picture there, you can see that the data is obviously following some sort of non-linear pattern or trend. So the relationship between your x and y variables is not linear. So you're breaking that assumption. And the way we can test this is using a residuals versus fitted plot. And this is something I'm going to show you how to do in RStudio. But the basics of it is that you want to see your data sort of randomly plotted on the residuals versus fitted plot. So on the left-hand side there, you can see the red line is straight across. It's a horizontal straight across line, and the data points are sort of randomly on the top and bottom and from side to side. In the middle plot, you can see that on the left-hand side of the plot, the points are fairly clustered together around that horizontal red line, and they fan out as you move toward the right of the plot. So in this case, it's telling you that your data is breaking the assumption that your model can be represented with a linear regression model. And the last situation is also showing you that your data cannot be explained using a linear model, because the red line now is no longer horizontal and it's showing a sort of curved pattern, and the data is sort of following that red line in that curved pattern. The second assumption of linear regression is called homoscedasticity. It's a very hard word to say. However, it tells you if the residuals have a constant variance. So it's assumed in linear regression that your residuals will have constant variance throughout the dataset. And the test we can use for this is called scale location. So in the plots on the slide, you can see that in case 1, we have a relatively horizontal red line, and you can see the points have a constant variance, so both vertically up and down as well as horizontally left to right around that red line. Whereas in case 2, you have a red line that's not horizontal, and you can see that there is more clustering on the left side of the red line, and it sort of fans out toward the right side of the red line. So you can see in case 2, that would break the assumption of homoscedasticity, whereas case 1 is fine. The third assumption of linear regression is normality. So do the errors or residuals of the regression model, are they normally distributed at each value of x on the regression line? The best way to test for this is using a QQ plot, which tells us the normality of the data for each value of x. So you can see there on the slide that there are these different outcomes, and each of these outcomes tell you a different thing about the residuals in your distribution. So a normal QQ plot will be a very linear line where all the points will be following a diagonal line from left to right. And you can see, based on the bend of the QQ plot, or the points on the QQ plot, they mean different things. So you could have a light tail or a heavy tail on your distribution of residuals, or you could have a skew from left or from right, or you could have a bimodal distribution, which means you'll have 2 or more peaks on your distribution. The last assumption of linear regression is that your residual error terms are independent of one another. So each individual observation in your data should be independent of the other points in your data set. And this isn't really an issue unless you're using time series data where the years before will predict or depend on the years in the future, or rather that the years in the future will be dependent on the years in the past. A final assumption of linear regression only is needed when you're using a multiple regression model. So if you have two or more independent variables, you should check if these independent variables depend on each other. So do the independent variables themselves depend on other independent variables in your model? Ideally, you don't want them to depend on each other, or at least not very much. And you can test for this using a variance of inflation factor. So the rule of thumb is that if your variance of inflation factor is less than 2, that means you don't have any real dependence between the independent variables. So that's good. If you have a variance of inflation factor that's greater than 5, that means you should definitely take out that independent variable from your model because it's overlapping with explanatory power of your dependent variable. So that variable specifically is dependent on other independent variables that you're using, and it can create problems with your prediction or explanatory power of your regression model. Now, when you have a variance of inflation factor that's somewhere in between 2 and 5, you're going to have to make some sort of judgment call about that independent variable. And it's key to understand the relationships of your independent variables with each other as well as with the dependent variable. So it depends on the data set that you're using, and you need to have understanding of how those different variables might influence each other. So if you have a variance of inflation factor that's very close to 5, you might still want to take out that variable from your data. So a question you might be asking is, well, how many independent variables should I actually add into my regression model? How do you know? The thing is that with a model, you're only trying to model or estimate or make predictions based on a simplistic model. So the more variables you add to the model, the higher your R² goes, which increases the predictive capacity of your model. However, the more variables you add, the more your model becomes what's known as overfitted. So overfitting is when you've added too many independent variables to your model, and it's predicting that specific data set very well. But the reason we create models is to predict other data. So we have a sample data set that we're using to create a model that can then predict outcomes that we did not observe. So if we've overfitted the model to a very specific data set, our predictions that we're making will really only hold true for that one data set. So let's say you're looking at predicting tree height, and the first variable that you have is the amount of sun that we've had over the course of the year. And let's say then you start adding other variables. You're adding canopy cover in the forest. You're adding air quality data. You add the amount of rain we've had. And you keep adding more and more independent variables. And then you've created a regression model, say using 10 different independent variables. And it's able to predict the tree height very well. Say your R-squared value or your adjusted R-squared value is 0.80. So you have a very strong regression model that's able to predict tree height very well. And then you take that regression model and you're looking at Hamilton, and you take the regression model to, say, Victoria, BC, and you're trying to predict tree height there. You might find that its predictive power in BC is not very good. You're able to predict tree height very well in Hamilton with those very specific characteristics, and you take a regression model to BC and it's not able to predict with the same ability. So when you add more variables to your model, you're overfitting the model, and your model will have less generalizability, and you aren't able to use that model anywhere else. And unfortunately, there's no real rule of thumb for how many independent variables you should add to a regression model, but it takes understanding of your data set and your variables that you're looking at to determine how many variables you should add. So in research, you would do a literature review where you're looking at other papers or other research to understand what variables might actually influence your dependent variable. And then based on your findings, you can make informed decisions about which independent variables to include. And to summarize, when do you actually remove a variable from your regression model? So the first one is when you do your regression model, the summary tells you that variable is not statistically significant. So your p-value, it exceeds your p-value of choice. So if you chose 0.01 as your p-value, then anything with a p-value above 0.01, even if it's 0.011, you would eliminate it from your model. If your variance of inflation factor is greater than 5 when doing multiple regression, you would eliminate it. Or based on your knowledge of the data and you made a judgment call when your variance of inflation factor was between 2 and 5. Or if your coefficient estimate is not expected. So if you expected the variable to be a positive result, you would eliminate it from your regression model if it was a negative coefficient. So that wraps up the lecture for regression modeling, correlation, and interpretation. And based on that lecture, I'm now going to do a tutorial in RStudio where I'll show you how to do all of these things and a little bit more interpretation. All right, so we just went through the lecture on correlation and regression, and now I'll go through a RStudio example of those concepts. So the first thing you're going to want to do is install the Broom and the GG Fortified packages. So Control-Shift-C, run that code, and then Control-Shift-C to recomment it. I noticed in some of your assignments you were having trouble knitting your RMD file to HTML. If you leave these lines of code as uncommented, so they're like that, when you go to knit it to HTML, it won't work. So make sure they are commented after you install them. We are going to load those libraries. Then we're going to remove scientific notation with the options function. And then we will import the data. So the data is the Internet Movie Database movies. And we're going to call that data frame movies. Now, one thing I want to talk about before we get into this should be a fairly short tutorial compared to others. However, I do want to talk about what these arguments mean. So in an RMD file, which is short for R Markdown file, it's a stylized means to display our programming code and their outputs. And typically you'll have just the R on its own, and that denotes to RStudio or your HTML file that this is a block of R code. So if you run this code without any of those arguments, you can see below it'll output the message about that data or that line of code and a warning about that code. So if you wanted to remove that top section, which is this information, and by the way, this information is good to know if you're actually working with the data. It tells you what each of the columns are, or the variables, and it tells you what type of column that is. So the year is a double column, which means it's a numeric column. Now, if the duration, say you wanted to use the duration column, say this was not a double and it was a string, then immediately you know that you need to fix that duration column. So that can be very handy. But if you don't want to see it, not only you don't want to see it in the R Markdown file itself, but you don't want to see it in the HTML file, you can do R and then comma and then message equals false. If we rerun this code, you'll now see the message isn't being shown. Now, if we wanted to remove that warning that we're getting, because we don't really care, we can do warning equals false. Now you can run that, and now nothing shows up. The movies is still, I'm just gonna clear that so it's not distracting. The movies data frame is still being imported, as you can see. Just gonna run that code before. You can see it's still being imported, but it's just not outputting any of the messages or warnings. Another handy argument you can add to that R kind of this area here is a argument called echo. So say you're creating a HTML document that you're going to be displaying on a company website, and you want to show outputs. You want to create a report, a really professional report, and you don't want all of your blocks of code to show, because some of them are just blocks of code that you needed to use to clean the data set, or you were removing scientific notation or something. You could use what's known as the echo argument and set that to false. And let me just show you. So let's create a variable called test, and we'll set it equal to 3, and then we'll output the variable 3, so it's going to output 3. So if we run that here, you can see it outputs 3. Cool. Now what does that actually mean though? So if we knit this to HTML, we're not going to see this block of code. We're just going to see this answer. So let me go ahead and knit this to HTML. It's going to take a second because there's a lot of code here. So you can see now under this import data, so you can see back here the block of code with the answer 3. You can see in the HTML, you still see the import data heading, but you don't see the block of code, you just see the answer. So this is another kind of powerful way to manipulate your output as an HTML or whatever. You can knit to PDF or a Word document as well. And it's a great way to manipulate your outcome so that it's displaying the way you want to display it. For the purpose of this course, you don't need to worry about it. In fact, I wouldn't recommend changing any of this from what I already have. You don't want to not display something that you should be displaying. But it is good to know for the future when you're working at a job and you want to manipulate your outcome. So this next block of code, or this next chunk of code, is cleaning the movies dataset, and it's creating a new one called budgets. Again, I'm not going to go through this because you should know how all of this works already. This chunk of code would actually be a great thing to use the echo false, because no one probably cares about seeing the chunk of code you use to clean the data set. So if we knit this with the echo, you would also remove the heading of cleaning data set. You would just put that as a comment if you were actually doing this. But let's just see, for the sake of looking. So yeah, you can see here, cleaning dataset. You would remove this obviously, but it's obviously a necessity to have in the RMD file for your code to run effectively, but your reader doesn't need to see this. In fact, all of this stuff is probably stuff your reader doesn't need to read, and thus you could use the echo argument to remove all of these chunks of code, which would then just leave your reader to see the important code. I'm just going to remove that though, because you guys do need to see the chunks of code. So we're filtering out the NA values from the budget column. We're going to only look at movies that were created in the USA. We're going to create a column called currency, which just tells you what currency the budget is in. So is it in Canadian dollars? Is it in USD? Is it in some other currency? And then we're going to extract the actual numeric value that is the budget. So if it's $1 million, it'll just take off the dollar sign and just leave us with the actual number 1 million. We're going to filter where currency is equal to the dollar. Just basically removes any movie that wasn't created in USD. And this is because I don't want to convert all of these movies' budgets into USD because I'm lazy and it's not important for an example. We're not doing real research. I'm going to also filter out movies that cost less than $5,000 to make. I just quickly learned that a typical production costs at least $5,000, so I don't want any kind of home movies to show up. I also want only movies that have 1,000 votes and only movies that were created beyond or in 2010 or beyond, so the last 11 years. And this is, again, an issue with money. I don't want to have to deal with inflation or limit the amount of influence inflation has. So that's just kind of maintenance of the data set to get it ready for us to use. So now we can see in the budgets data frame, has the title, the year it was made, genre, etc., and the budget in USD dollars. So, okay, to move on to the first measure is covariance, and we can calculate covariance manually with this math. And again, I'm not going to go through it, but you can look at it and do it on your own. So if we calculate covariance, it outputs 5,722,000 877. And basically that number just means that because it's a positive value, we know that as the budget of a movie increases, the average vote of a movie also increases. That's all that's saying, basically. But, why, bother doing all of this math when we can just use the covariance function that's built into R? So COV, and then we put in, because this is a base R function, we have to put in the data frame. So budgets, $ average vote, and budget USD. Run that. You can see it's the exact same number. It's because this function, this covariance function, is created with all of that math going on behind the scenes, essentially. It's a function that has all of this math in it, and it's doing all of that math, but it's built actually into the R programming language. And that's why it outputs the exact same value. So next we're going to look at Pearson's correlation coefficient to understand the relationship between the budget of a movie and its average vote a little bit more in depth than the covariance. So again, we can do the math on our own, and let's go ahead and look at that. Our Pearson's correlation coefficient is 0.31 in this case. So now we know, not only because it's positive, not only do we know that as the budget increases, our average vote also increases, but we also know the strength of the relationship between those two variables is fairly weak. It's somewhere in the weak to moderate area because 0.31 isn't really that high. Now, again, why bother doing all that math when we can just use a built-in function? So core.test is used to do a Pearson correlation. You can also do different correlation functions with this by specifying an argument. I think it's called method, where you can do Spearman correlation, or I think there's Kendall's as well. There might be others. Anyways, when we run this, we can see it's the exact same correlation output. So you can see 0.31 is the exact same as the other Pearsons that we calculated manually. So this value is the exact same as that value. This function is built in, and behind the scenes, it's doing all of that manual math. You can see the core.test function also outputs a summary of other important information. So the 95% confidence interval is saying that, well, looking at your sample, your Pearson's correlation coefficient for your actual sample is 0.31. However, if you're looking at the population level of all of the movies, you could expect a Pearson correlation coefficient somewhere in between 0.24 and 0.37. So that's what 95% confidence interval actually means. You can also see the t-value, the degrees of freedom, as well as the p-value. So not only can you calculate the Pearson's correlation coefficient much easier with a built-in function, it's also calculating all of this other information for you, which is even better. So now let's create a XY scatter plot of, on the y-axis, our dependent variable of budget. Our y or dependent variable is average vote. And on the x-axis, which is our independent variable, will be the budget of the movie. So I'm going to go ahead and create that ggplot. And you can see all of the black dots represent a movie, and it shows the budget and the average rating that movie received. This is on the high end, $75 million, and the review score goes from 0 to 10. you can see, just as the measures already told us that these two variables covary positively, so as the budget increases, so does the average score. You can also see the Pearson's correlation was 0.31, which tells us it's a weak to moderate relationship. And you can see the regression line is shown in blue. And you can see the black dots, which represent movies, vary kind of widely around that blue regression line. So it's not a strong relationship. And in this ggplot function, we have geom point, which creates the black dots. The geom underscore smooth is used to create this regression line, the blue regression line. So the method is lm. Lm is the regression function in RStudio. SE is the standard error. So if we change this to true and we rerun this code, you can now see this kind of medium gray area around the regression line, which tells us the error associated with predicted values based on that regression line. I'm going to go ahead and switch this back to false. We don't need to see that. All right, so moving on, we can now look at R squared values. So if you remember from the lecture, R squared is used to look at the strength of or the predictive power of our regression model when we're looking at a bivariate model. So when we have one dependent variable and one independent variable. So this LM function is how to create the regression model. So average vote is, so this is essentially the regression model itself right here. So average vote is our Y variable, so our dependent variable. And this little squiggly represents an equal sign. But because an equal sign specifically in RStudio, in the R programming language, is already used to represent, well, equals for variables, for setting variables, the LM function can't use an equal sign and thus uses the squiggly line or a tilde to represent an equal sign. So average vote, Y or dependent variable, equals budget underscore USD, which is our X or independent variable. And we're getting those variables from the budgets dataset. So if we go ahead and highlight the LM function on its own, Control Enter, it outputs the call, which is the formula that we used, and the coefficients. So the y-intercept and the beta coefficient for the budget USD. But if we wrap that function around by adding the summary function, so the LM function is within the summary function, and we rerun this, and I'm going to set it equal to the budgets underscore reg. So if we run this line of code, it'll create a variable called budgets underscore reg or regression and set it equal to the summary output. And then we're going to run that, and we'll see that it creates this big summary output of the regression model. And this regression summary is the exact same as the one I discussed in the lectures, so I'm not going to go through it again. However, what I will tell you is how do we extract information from this summary using code. So say we wanted to extract this estimate for the y-intercept. We could use this line of code right here. So let's break this down. So if we type in budgets, and as we're typing it, it pops up with the budgets data frame. We don't want that. We want budgets_reg. But the reason I'm pointing this out is because beside the budgets data frame right here, you know it's a data frame because there's a little table icon right there. Whereas the budgets_reg, because it's a summary regression output, it contains multiple types of data, and thus it is denoted by this little symbol with the yellow, blue, and purple. So we're going to click on that and then put a $sign, and you can see the variables are now showing up. So you have the call, the terms, residuals, coefficients, etc. And you'll notice beside call, terms, residual, R squared, adjusted R squared, etc., there's these little pinkish purple rectangles, and that denotes that it's a variable or a data value rather. And that means it's just one thing that you can return. It's one value. Whereas beside coefficients, you can see there's a table icon. And that's because the coefficients in the budgets_reg summary output is actually a table. And if we run this, you can see it outputs this little table where it has the intercept and the budget USD variables and the estimate, standard error, etc. So then from here, we can then extract variables or data values rather from each of the columns of estimate, standard error, etc. So if we do 1, 1, we can extract this intercept estimate. And we'll go ahead and do that, and you can see 5.8. Right. Now, if we did budgets_reg, $sign, coefficients, and then did 1, 2, it gives us the budgets. Let's go ahead and we'll run these 2 lines of code so you can see what it's selecting. So you can see here, it's looking at the first row and the second column. So this line of code here is selecting the standard error for the y-intercept. What if we want to select the data value for budget USD, the estimate? We'll do budgets_reg, $sign, coefficients. Then we'll do second row, comma, first column. And you can see there, I'll go ahead and run these 3 lines again so you can see. So 1, 2 is row 1, column 2, so that's that value. And then row 2, column 1 is that value. So that's what that means. So I'm going to go ahead and delete that and run these 2 lines of code on their own. So I now have extracted the y-intercept estimate and the budget USD coefficient estimate. Now from that, we can go ahead and calculate our R-squared value using the math from the lecture slides. And we can see the R-squared value here is 0.0977. Now, why bother, again, doing all of that math when we can just extract the R-squared value from the regression summary? So we can just do that with this line of code. And you can see it's the exact same value. So you can see they're the exact same value. We can either, basically the summary regression model is doing all of this math behind the scenes and it's outputting it as the R-squared value. And then down here in the inline code, so this inline code, it's taking the R-squared value and multiplying it by 100 and then rounding it to 2. And this value tells us that the budget of a movie in USD only explains 9.77% of the variation in the average vote. So it's not explaining much. So now to move on to an example of adjusted R-squared. So adjusted R-squared, if you remember, is used when we want to do multivariate regression modeling. So I'm going to create a new regression summary using average vote as our dependent variable, budget USD again, but we're going to add in the duration of the movie. So does a longer movie increase the average vote that it's going to get? And we add in variables into the regression model using a plus sign. So I'm going to go ahead and create the multi-reg summary of the regression model. And you can see down here, the adjusted R-squared is 0.2511. And it's slightly lower than the R-squared because although the R-squared increased versus our last model, so it increased quite significantly. However, the adjusted R-square, when we take into account that extra variable we created, it is still lower than the R-squared. The R-squared is being inflated by the addition of a second variable or independent or predictor variable. So the adjusted R-squared is accounting for that, and thus it's slightly lower than the R-squared value. But the addition of duration did significantly increase our R-squared value. So our R-squared value with just the budget was 0.0977. When we added in our duration, our predictive power of the model increased to 0.2511. And again, I'm not going to go through all of this, but the addition of more predictor variables will show up here. So duration is there. You can see all three of the estimates, so intercept, budget USD, and duration, all remain statistically significant to a value of p less than 0.001. Or you could just read the actual p value here. It's very low, as you can see. We can also manually calculate the adjusted R-squared using this math here, which also is shown in the lecture slides. I'm not going to go through it because you don't really need to know how to calculate these things manually when you can just do them so easily in RStudio. So I'm going to go ahead and run this. You can see, just like the summary, you're extracting the R-squared value, and then we're interested in the adjusted R-squared value because we're doing multivariate regression modeling. This line of code was just to find out the average vote, which I used in the lecture slides. It's not really relevant to what we're doing here. And this inline code, again, is telling us that the budget and duration of a movie can explain. Let's go ahead and copy, because I don't want to knit it because it'll take a while. I'm going to go ahead and paste it there. So the inline code will output this value right here, 25.11. So budget of a movie and the duration of a movie can explain 25.11% of the variation in average vote. So it's a much better model than just budget. So now we're going to move on to the last segment where we go over the assumptions of our linear regression models. So the first thing is I'm going to create a variable called model and set it equal just to the LM function of average vote and budget USD, so it's a bivariate model. Now I'm going to use this. This is really just to visualize the residuals. You don't really need to know how this all works. But we're going to use the augment function of model to create some information. I'll run it on its own so you can see what kind of information it's creating. So average vote, budget, and then it gives you all of these other sets of information about it. You don't really need to know that. And I'm going to create a ggplot. I'm just going to create it and then show you. So basically this is just showing you the red lines are indicating the residual between the movie, the observed movie data, and the prediction of the blue line is the regression line. So the red lines show the error associated with the prediction from the blue line, which is the regression line, and the actual movie observed data. So the red line indicates how far off the prediction of the model was from the actual review score of the movie. So in many cases, it's very far and the residual is pretty high. So it's not a great model. And so this is to create the black dots. This is to create the regression line. And this is to create those red lines for the residuals. Okay, so moving on, we are going to talk about the assumptions of a linear regression model. So linearity, homoscedasticity, hard word to say, and normality. We're not going to talk about independence because we're not using time series data, so we don't need to worry about it. And we can create all three of those plots all at once. So using base R, we can do this, and then I'm going to show you a ggplot style of this using a different package. So you can see here, this is the output from base R. You can see the plots, they're fine, but they don't look that nice. They look pretty old school. The one thing to note is the residuals versus leverage. You can actually see the Cook's distance line right here in the bottom right, whereas you can't see it in the ggplot version. So I guess that's something to note. But I'm going to create the ggplot styled one. So this is from the ggfortify package, and it just creates the same plots, but it's just a little bit nicer to look at. So the first plot in the top left is residuals versus fitted, and we use this to test the linearity of the data. So can we actually predict these values based on a linear regression line? So the blue line here is meant to be relatively horizontal, and we're supposed to see black dots, so the data points to be evenly spread top to bottom. And in this case, it does seem like the data points are fairly spread kind of constantly left to right, or top to bottom rather. And even though the blue line isn't completely horizontal, it is relatively flat or relatively horizontal. So I would say that is fine and expected. So the second plot we're going to look at is the scale location, which is the bottom left one. And this measures the homoscedasticity of our model. And what we're looking for is a blue line that is relatively flat, again, and supposed to have constant variance kind of top to bottom, And again, we see that, yeah, the data points are fairly constant in their variance top to bottom, which is good. The next plot we're going to look at is the normal QQ plot. And this measures the normality of our data set. And we can see the black dots are following the diagonal line fairly well. On the bottom left quadrant of the plot, we do see the data points kind of veer a little bit away from the diagonal line, but not so much that it's a worry. It means that there might be some light skewing of the data, but it's not too bad. And then lastly, although we didn't talk about it in the lecture, I did want to talk about what the residuals versus leverage tells you. So residuals versus leverage tells you if you have any outliers in your data. And that's what I was talking about when I mentioned the base R version of this. You could see basically if you have an outlier in your data, there are dotted lines that will show up if any outliers are present, and the data point will go over the threshold of those lines. So if we look at the other version of this, so if you run code with multiple outputs, it'll create these kind of panels that you can look at. So you can see in the residual versus leverage, down here in the bottom right corner, you can see a 0.5. You can just barely see a little dotted red line. And that's indicating the line at which a data point exceeding that line would be representing an outlier in your data. This dotted line over here is just saying that's a dotted red line indicates Cook's distance, which is the line at which a point exceeding it would be considered an outlier. So that is how you look at your data and see if any of the assumptions are broken. Now let's look at a multiple regression model. And we're going to kind of go over the same things, but for a multiple regression model. So let's have average vote be our dependent variable again. Budget USD is our first independent variable. Then we'll have duration. We have Metascore, reviews from users, and reviews from critics. And this is all still coming from the budgets dataset. And we're going to create a variable called multi_model to indicate that it's a multiple regression model. So again, we're going to, this is the base R version, and this is the ggMortify. I'm going to run both of them just to show you the leverage again. For the purpose of the assignment, you just need this one auto plot. This is all you need, but I want to show you the leverage plot. So you can see on the leverage plot for this multiple regression model, you can now clearly see those dotted lines that I was talking about. So they extend on the top and the bottom. And if you had a outlier in your data, it would be in the top right or bottom right corner, and it would exceed that Cook's distance line. So that's how you read that plot. But I guess to be clear, I'll just run this auto plot. This is all you need for the assignment. So again, residuals versus fitted. You can see the blue line is relatively flat, and you can see the variance in the data plot, or the data points, are pretty mirrored and symmetrical, top to bottom and left to right. You can see the scale location is showing it's a little bent. The blue line is a little bent, but it is still relatively flat. And you can see there's constant variance laterally and up and down. The normal QQ plot is again showing a little bit of a skew, but it's not bad. It's still following the line pretty well. And then again, the residuals versus leverage is showing that there doesn't seem to be any outliers in the data set. Okay, and the last thing I want to show you is the... Oh, sorry. Okay. And the last thing I want to show is variance of inflation factor. So this comes from the car package, which is technically built into the RStudio. And it contains a couple of functions and some data sets that you can use without having any packages installed. And in this package comes the variance of inflation factor function, so VIF. And if you try and run this on its own, it won't run. It'll say that it can't find the function VIF. But if you specify that you want to use the car package and you run this line of code all at once, then it outputs the data. So what this is saying is from the car package, and then 2 colons. So 2 colons right here, and then the function, and then you run it. So it'll read the VIF function, and it'll look in the car package. So if we run this, we can see these are all of our independent variables. So we have budget USD 1.38, under 2, all good. Duration 1.45, under 2, all good. Metascore under 2, good. Reviews from users under 2, good. Now we have reviews from critics, which is a 2.49. Now, as you remember from the lecture, any variance of inflation factor between a 2 and a 5 should be something that you take into consideration and you review and consider dropping it. So the important thing about making this decision is having an understanding of your data. Now, this is a data set from the Internet Movie Database. We know what the budget is. It represents the production cost of the movie. The duration, which is how long the movie lasted for, so like 90 minutes on average. Metascore is the review from critics specifically. It's a little bit more complicated than that, but basically it's a review or the average review based on critics only. Reviews from users is the number of text-based reviews from just the average person. So if you went on to IMDb, you could write your own review for a movie. And reviews from critics, the one that's greater than 2, is text-based reviews from people that review movies professionally. So because we know that reviews from critics and Metascore are sort of based on the same information, you would expect these two variables to be dependent on each other. So although 2.49 is still relatively low, it's only barely above 2, we do know that the reviews from critics and the Metascore would be dependent on each other because they're both reviews based on a professional movie critic. So in this case, because we know that these two things in theory probably do depend on each other, we're going to go ahead and take out reviews from critics from our model. If you weren't so sure about the relationship between those two variables, I would not suggest taking the variable out because 2.49 is still a very low variance of inflation factor. But because we know that these are two variables that probably overlap each other, we can take out the reviews from critics. So now we can rebuild our multiple regression model, and we can rerun the diagnostics to see how that affected our model. So this model is the exact same, except I just removed reviews from critics from the model. Let's run that. Good. And we're actually going to create a summary. So let's do summary, and we'll copy this, paste it in, and run that. And we can see now, upon further review, that the reviews from users is not statistically significant in the model. So we're also going to drop reviews from users as well. You can see the residuals of our model are much better. The minimum value is a lot less, not significant, but it's a lower value. I think before it was negative 4.4, and now it's negative 2.8. So the model is better at predicting movies. And the maximum, I believe, is also lower. The median as well is closer to 0, which is good. And the first and third quartiles are also closer to 0, which is also good. And our adjusted R-squared, although we need to remove this variable, our adjusted R-squared is much higher. It's now 0.6092. So if we go ahead and take out reviews from users as well. So let's create a new model here. Multi-model underscore v3, and set it equal to this, and then remove that. We have that. Let's get a summary of it. See how it changed. Create a summary of it. Now we can see everything in our model is now statistically significant. So our y-intercept, our budget USD, duration, and Metascore are all statistically significant. Our adjusted R-squared value is still 0.6097. So that reviews from users wasn't really doing anything to enhance the predictive power of our model. And the residuals are the same as well. So this would be our final model, but we're still going to look at the diagnostics for it. So I'm going to, instead of changing all of these V2s to V3 manually, what I'm going to do is select all of this code, go Control F, and make sure in selection is checked. And I'm going to look for V2 and replace it with V3 and click all. So it's going to look for V2 and it's going to replace V2 with V3 every time. It tells you nine times that it did that. So let's go ahead and run the auto plot. You can see residuals versus fitted. It's good, pretty horizontal, pretty constant variance. Scale location, same thing, pretty horizontal, pretty constant variance. Normal QQ, it's still slightly skewed, but that's okay. And our leverage is fine, there's no outliers in our data. We're going to now look at variance and inflation. You can see the variance of inflation factors are all very low, so none of these independent variables are being explained by any other independent variable. That's good. And I'm going to delete that because it's no longer relevant. And I'm going to take this variance of inflation and create a variable called VIF underscore R underscore V3. And then based on that, we can output the variance of inflation factor for budget USD, duration, and Metascore. So if you wanted to report the variance of inflation factor for any of those outputted in this, so in this, it outputs basically a little chart. And if you wanted to extract those data points, you can use the double square bracket with 1, 2, 3, and it will extract them separately. So you can see if you run all of this at once, it says the square bracket's 1, it's extracting this one. Square bracket's 2, it's extracting the duration. Square bracket's 3, extracting that one. So that is all I need to show you for this tutorial. Much shorter, I think, than the other tutorials. This tutorial is much easier, and I think it's starting to really show the power of functions that are actually built into R. You don't have to do all of the manual math from the lecture slides. You can just use one function that's built in. And I hope this tutorial again helps you, and good luck with the assignment.